We have 2 standard deviations above the mean, so we have to add that again. And if you do that, we should get 4.53. So really, we want to know the probability that x, our random variable, our random binomial variable, is more than 4.53. More than, that's greater than, okay? It's not greater than or equal to, more than. So if I'm looking at this, 4.53 is right here, okay? 4.53. If they got more than that right, that would mean they had to have gotten somewhere from 5 to 10 right? Right? So I want to find the probability that x is what? Greater than or equal to 5, which is 1 minus the probability that x is less than or equal to 4, because you can't have things between 4 and 5. Either you get 4 right or you get 5 right. You can't get 4.53 right, okay, even though the statistics worked out that way. So I want to find this. So this is binom CDF, binom CDF. Let's see if we do it right. Okay, we get to our good old calculator. And I do second dister. Binom CDF, how many trials? 10. P is 0.2. And we wanted what? 4. And then I hit enter, enter, enter. 0.9672. So, equal to 1 minus 0.9672. Is that what I said, or 9762? Nope, 9672. And then I do 1 minus that, 1 minus 0.9672. And I get 0.0328. 0.0328. Hopefully you guys got that. Hopefully you got it. You guys are pretty good. I'm confident you got that. Or at least you could set it up. Okay, at least you could set that up. All right. Move it along. Sampling without replacement. So we've talked about the importance of sampling with replacement. Okay? If you are taking stuff from, I don't know, if you are choosing from a deck of cards or doing some type of probability experiment, your probability changes. Like if I'm taking the probability of drawing an ace and I draw my first card, the probability is 1 out of 4. If I don't replace that, my probability changes for the next one. And when we're talking about small numbers, small sample sizes, then replacement is very, very important. Okay, but what we're learning here is you can sample without replacement, okay, as long as your sample size, okay, is less than or equal to 10% of your population, okay? So if you were at this, factory that made, I don't know, they have quality control things for everything. Let's say they had a cell phone. They were making a cell phone manufacturing plant. And let's say that they made, I don't know, 4,000 cell phones a day at this place. And you wanted to sample, and you wanted to sample without replacement. Well, you could take a sample of 10 because your sample size is so big, okay? Because your population, excuse me, your sample size would be like 4 that you chose. The population is so big. So as long as your sample size is less than or equal to 10% of your population, you don't have to worry about replacing, okay? And we're going to see a lot of examples on that. You'll see, especially chapter 7. So it says that batteries, almost everyone has one, a drawer that holds miscellaneous batteries of all sizes. Suppose your drawer contains 8 AAA batteries, but only 6 of them are good. You need to choose 4 for your graphing calculator. If you randomly select 4 batteries, what's the probability that all 4 batteries you chose will work? Explain why this is not the actual probability. Okay, the actual one is 0.2143. And the reason for that is because your population of batteries there is 8, and you're choosing 4. So you didn't talk about replacement here. We're talking about a very small population, okay? Again, if you're going to do it without replacement, your sample size needs to be less than 10% of the population. If I choose 4 as my sample size out of a population of 8, that's like a 50%. Okay, it's got to be less than or equal to 10%. Okay, so that's why that probability doesn't make sense. Okay? All right, I'm going to stop it there because we're going to finish this. Actually, am I going to do the next part? Yeah, I'll do the next part. So it says the normal approximation for binomial distributions. So it says, suppose that a count X has the binomial distribution with n trials and success probability. What that means. When n is large, the distribution of X is approximately normal. So there are times when you can use the normal approximation to approximate the binomial distribution, okay? And this is our rule of thumb. When n times p is when you have more than 10 successes and more than 10 failures, okay? So you do n times p and n times 1 minus p. When that happens, they say that you could use the normal distribution to explain the binomial probability, okay? Or the binomial random variable. So let's look. Ready? Here we go. This is a preview of chapter 7, okay? So they say you don't have to really do this, but when I know that we're doing this in chapter 7, it makes sense. It's going to be easier when we get there. This is going to be one of our conditions. If I slide this down, this is going to be one of our conditions in chapter 7. Okay, so we're going to start that now. And you're going to say, oh yeah, I remember that when we get to chapter 7. Teens and debit cards. Talk about a dangerous combination. Teens and debit cards. In a survey, 506 teenagers, ages 14 to 18, were asked a variety of questions about personal finance. One question asked teens if they had a debit card. Suppose that exactly 10% of teens have debit cards. Let X equal the number of teens in a random sample of size 506 that have a debit card. Show that the distribution is approximately binomial. Okay? So, that's BINS, guys. B-I-N-S. You don't need me to do that. I'm going to give you guys a couple of minutes to do that. Okay? You don't need me for that. You can do it. I know you can. A lot of talking today, boy. I'm filming videos like crazy. Okay, so let's check that out. You guys should be good with that. I'm hoping. This is next. This is my next video I'm filming today. Some of you guys might be in here. Okay, I'm going to start filming these videos. We're a little less than a month away. Gotta get a head start. Hopefully basketball is going to start. I'm hoping, man, I'm hoping. You guys will know, by the time you watch this, you'll know basketball will already start. I'm hoping. Show it's approximately binomial. All right, here we go. So, binomial, what are they saying? Kids have a debit card or they don't? Check. Whether or not one kid has a debit card has no bearing on whether someone else does. Okay, so students with debit cards are independent. Number, what do we say? What's our sample? 506, I guess. N equals 506. And then the probability of success, it says 10%. 10% of teens between 14 and 18 have a card. All right, so there we go. Now, part B, check the conditions. You guys gonna do that too? N times P greater than or equal to 10. N times 1 minus P greater than or equal to 10. Check them. Check them. Check the conditions. Check the conditions, man. You got this. You got this. All right, let's look. N times P. N is 506. Times P is 0.10. So what's that going to be? That's 50.6, which is greater than or equal to 10. That checks out. N times 1 minus P. Well, we know that's gonna work, right? N minus P is 0.9. Okay? And when I do that, I should do it out. Let's be accurate. Let's be accurate. 506 times 0.9, 455.4. Greater than or equal to 10, check. Check the conditions, we did it. We can use the normal approximation. We use the normal approximation. Okay? Part C. Use a normal distribution. Yay, chapter 2. To estimate the probability that 40 or fewer teens. Well, let's look. Little normal model. You know, I don't know what to put in the middle yet. What do I put in the middle? My mean. I didn't find my mean. Well, we can find the mean. Mean is n times p. So that's going to be n is 506 times p is 0.10. So I get 50.6. Stuff goes here. 50.6. Standard deviation. Okay. Standard deviation is the square root of n times p times 1 minus p, which is 506 times 0.1 times 0.9, and then take the square root of that. 506 times 0.1 times 0.9, 45.54, square root, 45.54. I get 6.75. Let me just make sure. Yeah, 6.75. 6.75. So what do I have here? I have normal distribution. My mean is 50.6. My standard deviation is 6.75. So if I want to cut off my tails and split my uprights, draw an accurate picture, 50.6 minus 6.75 is 43.85. 43.85, sorry for the smallness. 43.85 minus 6.75, 37.1. So I know 40 is somewhere in here, and I gotta shade this. So we do norm CDF. I wanna find from here to here, negative 999 to my z-score. But guess what? I didn't even find the z-score yet. I gotta do that first. So let's erase some of this stuff up top. And let's find the z-score. Okay, I can't go any further. Can't go any further. So my data value is, what is it, 40? 40 minus 50.6 divided by my standard deviation. So 40 minus 50.6, negative 10.6 divided by 6.75, negative 1.57. So that's what I gotta fill in here. So second bars for Dister, norm CDF this time. Negative 999 to negative 1.57, and then ding, ding, 0.0582. 0.0582. Let me just check my answer and make sure that we did that correctly. We did. Okay, so that's, if we had a sample, the problem, if 10% of teens between the ages of 14 and 18 have a debit card, the probability of getting a sample of 40 or fewer that have a debit card would be 0.0582. Okay? Next up will be the geometric distribution. That will be next.